Hello, my name is Marcus. I'm going to present my PhD research project. I'm a third year PhD student in geophysics, and my advisor is Dr. Heather Bido. Um, it's about machine learning using seismic attributes and well dynamic data applied to subsurface reservoir productivity and activity prediction. So the presentation outline we're going to have sorry, this point here, the laser pointer. So introduction and motivation, the problem overview, data sets and methods, the results so far I have, next projects, and the preliminary conclusions. So to begin, let's start with this quiz. Prove you are human and select only the images with highly productive carbonate mounts. As you can see here, this is a task is very difficult because we have bunches of mounts here and they are pretty similar to each other. You've taking a look only at the seismic amplitudes, but three of them they are not carbonate buildups. This one is a pseudo buildup related to tectonic deformation. This is a volcanic clastic mound, and this is a volcanic mound. So all of them were drilled, and we have three pitfalls here that we want to avoid. This is a problem, not only a Petrobras problem in the Santos, the Brazilian deep waters of Santos Basin, but all our other competitors' problem as well. This is an industry problem that must be overcome. So the motivation is in some of the industry offshore projects, from field discovery to first oil production, it takes up to 10 years. So this delay is mainly caused by drilling bad wells during appraisal phase, either due to seismic imaging issues or due to ambiguity pitfalls. As a result, the more time you spend on appraisal and development drilling, the more economic value of the project will be eroded. And the solution, we are proposing to use the big data analysis, seismic and wells. Seismic data is big data, and machine learning techniques for reservoir sweet spot identification to optimize exploration, appraisal, and development drilling to bring this time as close as possible to 3 years from discovery to production instead of the 10 years, instead 10 years. So the idea here is to work with using my interpreter experiences and well data, mainly dynamic data, well test data, DST and PLT. DST is Duration test data and production logging tool. Seismic attributes, but early exploration phase seismic attributes, though the classic attributes derived from a full stack volume, no inversion data because seismic inversion data they are reliable only after the drilling dozen of wells to have an accurate wavelet estimation, which is not the case in the early exploration phase areas. And to use machine learning to combine those data using machine learning, supervised or unsupervised. Unsupervised, you can have seismic facies cubes, and supervised, you can use it to do, for instance, as supervised regression of flow capacity and build a 3D seismic cube for prediction. So the data set, the main data set I'm working with is from the Mero field in Brazilian deep waters. It's a giant field. It was discovered by Petrobras in 2010 by Petrobras and the ANP, the Brazilian agency, and since 2013 it's being operated by Petrobras with all partners, which is Total, Shell, SNOOC, SNPC from China, both of them from China, and the Brazilian government representative. And it's a light oil field with up to 40% of CO2. This CO2 is being re-injected in the reservoir for EOR purposes. So this area, this meadow field, is a very interesting one because we have a lot of uh, well information. We have well test data and production history as well. And it is adjacent to an underexplored area, which is the Central Libra area, which we have only 2 wells drilled so far, one discovery well and one dry well. And both areas are covered by the same seismic survey. So in this way, we can any machine learning pattern identified here can be immediately extrapolated to the Central Libra area. Okay, the main reservoir is are lacustrine carbonates from the Baja Valley Formation from the post-rift phase during the after the Aptian rift. Okay, and the main producing reservoirs are related to buildups and mounts heavily silicified, modified from a regional hydrothermal event, which has affected mainly the pre-existing porous system. So mainly in the buildups here, those are the main producers. We have also producers from the platform phases. It's basically uh, reworking of the sediments in the adjacent platform as many grainstones interbedded with spheroids and uh, uh, algal carpets. Okay, and the non-reservoir phases are related. The depositional lows related to embayment phases, which is composed mainly by magnesium-rich clays and spherulitites. And here we have the hydrothermal vents, which is the same, which affected here the buildups, but here they are less influent because they are very localized within the faults. And as here we have low permeability lithologies, those hydrothermal vents does not affect the reservoir as they affect here. It's a very local effect. And here we have the mounts and the platform faces as well. And in here in this the matter field, we have a lot of igneous bodies of Santonian age, which is intruding the reservoir, which is a problem. It's a drilling problem, and it is a flow problem because they are flow barriers. Okay, for the petroleum production. And this, as this, the hydrothermal alteration is driven by silica-rich fluids. So here we have silicified buildups, and these silicified buildups, despite they are very productive, they are hard to drill because the silica. Okay, so we have a lot of problems with drilling those as well. It's worthy to have in mind before the drilling what you are about to drill. Okay, so this is the general overview of the field. This is the model I've just told you, and this is the general view of the field. Here we have the meadow field here. This section is here, passing by the meadow field here. It's passing through the main platform area related to basement horsts here. The main unit here is the Baja Valley Formation in light blue, intruded by the seals. And here we have a secondary unit, which will not be the object here, which is the coquina. So we will be focused on this formation here, the Baja Valley Formation. Okay, and here in the Central Libra area, we have this field, which penetrated a intensely silicified buildup close to deep faults here. And this well encountered distal limestones with no porosity and intruded by seals. Okay, and these are mild productive wells in the meadow field, covered, sealed by a thick salt layer, kilometer thick salt layer. It's a very, very impressive petroleum system. Okay, so the data set, wells and seismic data. So this is the original seismic data set here. It was cropped in this area. In here we have a lot of wells, so more than 30 wells. The wells in blue were used for training for the supervisor learning, and the wells in red, they are used as blind tests for validation of the machine learning models. And the wells in black, they are semi-blind tests because we have no well test data, but other reservoir quality indicators, okay? So this is the seismic acquisition parameters. The main parameters are they were acquired before any production started. So it's looking as the reservoir was before production. And the maximum, it's stream powered. Okay, the maximum offset is it's 8 kilometers. Pretty dense beam size and narrow as so we are working with narrow azimuth data. We have limitations, but this is the most common kind of seismic data available in early exploration phase data. Okay, and this is the wells and seismic data. This is the cropped version and of the as I told you, we cropped around the area of interest, the meadow field, and the Libra area, central Libra area. So this is the cropped version of the seismic input, volume input. So here are the dimensions around the reservoir here. This is this east-west dimension of SOLV. So each attribute has 2 gigabytes. So here the bin size is 25 by 25. The sample interval here is 5 meters. And this is the total number of traces and total number of voxels. Actually big data because any machine learning uh, 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 prediction is doing in this huge amount of voxels. Okay, so this is the data, the well test data from the meadow field, from the Barra Velha formation. Okay, so all values here related to the well test data. So this is the flow capacity from the well tests, from the DST, drill stem test, and this is the productivity index. Okay, as you can see here, we have a very good linear correlation. It's curved because here the scale is in the logarithmic scale, but we have a very high correlation, linear correlation, almost 95% of correlation between flow capacity and productivity index. And as you can see here, we can classify those reservoirs in terms of productivity. So here we have the mild producers, low energy platform phases, which can produce up to 8,000 barrels per day. So they are very productive wells if you compare to onshore wells of shallow waters and other wells, tube diets, but they are less productive here. And as you can see, those related very low productivity productivity index and lower flow capacity volumes. We have the good producers, higher energy platform phases related mainly to the grindstones. These wells can produce up to 24,000 barrels per day. And here we have the hyper producers, the anomalies. As you can see here, we have box plots of both flow capacity and productivity index. We are talking about to these anomalous values. They are very high permeability buildups. They are silicified, but as a result of the silicification, we have an enhancing in the porosity system. It's cave porosity, it's calcified buildups. With here we have the flow capacity values explode for up more than 100,000 millidarcymeters and more than 1,000 productivity index. The productivity index over 1,000. So that's what we're talking about, those anomalies. And as they are very highly horizontally, vertically connected reservoirs here related to the buildups, with vertical wells, we can have flow rates as high as close to 50,000 barrels per day. And for instance, this is the production system. The FPS show present at the area, its capacity is around 180,000 barrels per day. It's to fulfill this capacity, it's only 4 pairs of this kind of wells here, vertical wells, to fulfill this huge FPS show. So it's very interesting to identify these kinds of reservoirs as early as possible in the project timeline. So this is the input seismic attributes I'm working with. So this is the input seismic attributes confined at the main reservoir level, which is the Barra Velha. Here we have the depositional model. This is the top of reservoir map, and here we have 3D view of each seismic attributes. Here it's the Hilbert transform of input amplitude. It's a mimics seismic bandwidth P impedance, so it responds for both porosity and clay content. This is the Hilbert transform in AVO attribute, which responds for porosity and clay as well. This is the sweetness, porosity, clay content, crusts, and fracture attenuation. The energy ratio similarity, it responds for folds, fractures, and classification. GLCM energy, lateral uniformity of reflectors, GLCM entropy, reflectors disorganization, and homogeneity, which reflector measures reflector smoothness. And average frequency, seismic attenuation related to fractures plus classification, and K1, maximum positive curvature related to convex mounts, and the K2, maximum negative curvatures, measure reflectors concavity. It's good to map the concave ponds. So, general research question, the main one is it possible to predict reservoir productivity using post-stack classic seismic attributes and machine learning during the early phases of subsurface project when only few or no wells and seismic inversion data are not available? So it was addressed by my first project, which is the project one. I worked with unsupervised learning. So is unsupervised learning useful for qualitative reservoir prediction in Brazilian pre-salt carbonates? And the second question is related to the second chapter and project. Is supervised learning useful for quantitative reservoir prediction? And the third one, related to the third project chapter, what about deep learning? Can it perform a better job than the shallow learning methods at a which cost? And can both shallow and deep learning be transferred across different data sets and areas geologically roughly similar? And can they discriminate volcanic classic from productive carbonate buildups? That are questions that are about to be uh, answered. So in my chapter one, I used mainly unsupervised learning. I used k-means, clustering, self-organizing maps, and generative topographic maps to predict facies. Okay. In the chapter two, I used classic supervised learning. Okay, for regression, supervised regression of reservoir properties related to the well test, mainly flow capacity and productivity index. I used k-nearest neighbors, okay, support vector machines, and random forests. And in the third chapter project, I'm going to explore the deep neural networks, okay. And in the chapter one, I use unsupervised learning cluster related to the k-means, SOM, and DTM. And chapter two, I used the supervised learning, random forest, k-nearest neighbors, and the support vector regression. And this is the results of the first chapter, unsupervised clustering final models at the Barra Velha carbonates. So I built 4 models. The first model, I use SOM and 6 input attributes to build this model here. Okay, and this is the 2D color bar. So here, as it's unsupervised, I interpret the results. So here we have the clusters related to the mounds, buildups, the most productive reservoirs, and this is the platform faces and bandment faces and the igneous intrusions. So it was very good to predict the occurrence of the igneous intrusions. Here we have a second model. I used the SOM with 8 attributes, GTM with 6 attributes, and K-means with 6 attributes. They are very similar each other. And this is a 3D view of one of the K-means clusters. So here we can see the 3D, they are transformed into geobodies. So here we can see the geobodies related to the most productive reservoirs, where most of the oil comes from. Here we have they are these blue geobodies penetrated by those wells. In the supervised learning models, we use the wells not for training because it's unsupervised, but we use them to validate our models. So here we can see the yellow wells penetrated those very productive reservoirs. So they are used to validate our models. Okay. And in here, we have in the central library, we have identified appraisal candidates for further drilling. Okay. So this work was published in the Marine and Petroleum Geology. We presented it at the Image Conference as well, and we presented in the AAPG conference. So it's widely published for the academic community. And the answer is yes, it's possible to do qualitative reservoir prediction in Brazilian pre-salt carbonates. Okay, we use a combination of 6, 8, and 10 attributes, and it was possible to discriminate seismic phases related to the hyperproductive reservoirs and the platform and distal phases and the igneous intrusions. Okay, and these are the results. They provided similar results, but K-means took 1/5 of the computational time. So this is relevant because when we work with very big data sets, so these have a great impact. While the other algorithms took 1.5 hours, this one took 0.35 hours, okay, which is about 20 minutes. So this is the project 2. In the project 2, I'm using supervised learning to train algorithms of supervised regression to predict flow capacity, for instance, both flow capacity and productivity index. So here, I'm using mainly this data from the PLT, which is a tool. So this is the tested interval. Here we have the NMR porosity. As you can see here, this reservoir is porous as a whole, from bottom to top. But when we use this log tool here, which is a spinning, which identifies the different flow velocities, here in the bottom, not a single drop is being produced from the well. Here we have a little bit, and here we have a huge gradient in the velocities, which showing this is a very productive zones, and 98, almost 100% of the oil comes from this upper zone. Okay, so these are the flow units interpreted from these tests and from the production logging tool. And as you can see here, those units have thicknesses that they are very close to the seismic resolution. Here we have about the decameter scale. Here we have 50 meters. We have decameter flow units of 30, 40 meters. So they match the seismic resolution. Okay. So for this reason, we are using them and seismic attributes to predict flow capacity. So this is the data. So The wells in red, they were using for training or supervised learning algorithms, and the wells in white were used as blind tests. We have test data, but they are not used for any training. They will use it for the validation of our models. And we have semi-blind tests as well. We have no DST data, but we have other reservoir quality indicators. So this is a detailed view how we build the training data set. So around each well, each tested well, and at the tested interval, we have the attribute, just one attribute, for instance, but we are working with 10 attributes. So here is the tested interval. This is the bin size, 5 meters by 25 by 25. So we pick the 9 traces around one well. And here at the same interval, we have the flow capacity values from the well test and the productivity index as well. We did it for 10 wells, 10 attributes. We have near 5,000 data points, training data points. So this is the correlation between the seismic attributes within the training data set, which is important to see. Here is the correlation scale bar. So red is one correlation, very highly correlated, -1 as well, very highly correlated. And it's good to these values keep around 0. Okay, so that's most of the attributes, they have very low correlation each other. The exception is the texture ones, which we have a kind of high correlation, but they are not redundant. As you can see here, the correlation here is about -0.6, so they are still, they can complement each other. So exploratory data analysis, let's take a look at the pair plots. So here we have the pair plots, which are the cross plots between each seismic attributes. And as you can see here, this is the hue is the value of the flow capacity. So as you can see, data is not linearly separable. As you can see, there is no correlation between the attributes, very low correlation. And when you take a look at the histograms from the attributes for the Baja-Velha at tested intervals, it's very difficult to separate the most productive from the non-productive as well. So showing that there's a lot of overlapping related to the ambiguity. So if you use one attribute at each time, you cannot predict. So you need to use all of them together to start making predictions. So this is our first result. So we using supervised regression for productivity index and flow capacity. This is our first one. We using random forest 10 attributes to predict flow capacity. This is the training accuracy and the blind test accuracy. Training accuracy about 85%, blind test 80%, not that bad. Uh, so we are dropping some attributes to reduce the dimensionality. So same model with 9 attributes, not a significant drop in the accuracy. 8 attributes, not a significant drop in the accuracy as well. All the way down to 6 attributes. So with random forest, with 6 attributes only, we got a training accuracy of 82% and blind test accuracy of 80%. So not a huge, not an impact at all of dimensionality reduction. Okay, you can work with less attributes. And same, we compare it across different estimators. We comparing with KNN, very similar. But when you go to the support vector machines, they are kind of overfitted. And we did the same thing for the productivity index. So very similar accuracies between KNN and in terms of blind test accuracy, okay, and random forest, but support vector machines, they are prone to overfit. And finally, we apply the same attribute combination in random forest with attributes after spectral balancing, so we have a improvement of the blind test accuracy up to 85%. So that's it. This is our model's accuracy between 80 and 85%, which is good. We are talking about two simple seismic attributes, no seismic inversion related ones, okay, and well test data. So in terms of time, KNN and random forest took about 1 minute, and support vector machines took 30 minutes for the prediction. So, and they are prone to overfit. So the best one, in my opinion, here is the random forest. Okay. So this is the random forest regression, a 3D view of the model. So the wells in red, they'll use it for the training. In white, they are blind tests. So here you're looking at the values, the hyperflow units relate to the hyperproducer as well. So as you can see, we have a very good match of our models. So 80% of the blind test accuracy here, and this is the attribute importance of random forest. So this is the most important ones is average frequency, K1, K2, and energy ratio similarity, which makes total sense because it's mainly related to the attenuation of related to the fracturing and classification and the shape of the mounds and buildups and the presence of fractures. Okay, so this is the sharp explanation. So this is how each attributes impact the model. So high K1 values yield to high flow capacity, low frequency yield to high flow capacity, low pseudo impedance, high flow capacity, low similarity, high flow capacity. So this study was submitted for interpretation. It's under review, okay, and we can answer. So supervised learning is very useful for quantitative reservoir prediction because with random forward regression using the 6 attributes, it was possible to predict flow capacity and productivity index with accuracies ranging from 80 to 85%. Neither AVO nor seismic inversion was needed to do so. Okay. And the next chapter will try to use the training from the METO data set to predict here in a very far away data set from the Bacalhau field. And so far we use it unsupervised and supervised. We are also going to test deep learning and transfer this learning to make predictions here when we have a challenge, the presence of volcanoclastic mounts. So the geology here in the Bacalhau field is similar to the Meru one, but here with the difference we have the Paraty basalt at the base of the reservoirs, and we have Sim depositional, Sim Barra Velha. At the same time we have the deposition of these very productive carbonate buildups and mounts. We have the occurrence of volcanoes, volcanoclastic edifice related to this magmatism, the later phases of these magmatisms. So they form mounts, and they are, in terms of seismic amplitude, they are very similar to this one. But this produces nothing, no reservoir at all, and here they are very productive. So this is one example from a couple wells in that area. So we have this well here, which drilled at a very big, huge mount, very good reservoir related to the buildups from the stromatolites and highly silicified. Here is one pitfall. So this is a pseudo buildup. It's related to tectonic inversion. So here we have only platform faces, not very productive, lower productivity index and flow capacity, and low energy platform faces here as well, not productive at all. And here we have other 2 wells here, another build up here, very productive one, another one very productive, and this one drilled a very beautiful build up, but related to the volcanoclastic. So only in the very top we have these very low values of productivity related to low energy platform. So we're gonna use the method training and try to predict the flow capacity and productivity index, and we use these wells as blind tests. Okay, so the conclusion so far with supervised learning, it's very useful for qualitative prediction. Okay, it was addressing chapter one. It was published in for the academic community. Research question two. Yes, it's possible to make quantitative prediction using supervised regression, mainly with random forest, using six attributes. We got pretty high accuracies, and we've used spectral balancing to improve the seismic the seismic resolution. We got higher accuracies of 0.85, and neither inversion or AV nor AVO were needed. It was presented at Image 2023, and it was submitted for interpretations under review. And the next research, we were going to predict the productivity at the Bacalhau field. We're working with learning transfer and deep learning, okay? And try to predict the occurrence of the volcanic mounts, okay? And see whether or not machine learning can address this problem properly, which is the next chapter, okay? So we're gonna look for deep learning, okay, and make the same techniques and attributes testing in meta field and use the meta field training and see how we can transfer this learning to make accurate predictions at Bacalhau field and anywhere in the basin, okay? So this is the research plan, what's been done so far. So the last 2 years I've been working with chapter one and chapter two projects. You know, recently I've started working with my new data set from Bacalhau, and this is the plan. So I spend the next 1.5 year working in this project, okay? And by the end near the end of this year, after the summer, to write my third manuscript and wrap up thesis for dissertation defense on spring 2025. Thank you so much. Okay, and enjoy